So let us move one step forward, and we are talking now about E. You all know what is E. Is the Nepper's number. You know, it is a sort of natural basis for the exponential, and so the natural basis for the logarithm too. And but I want you to know another application of E, and the subtitle is the following: How to make money by cheating with banks. It's always good to know how to make money. But you know, banks are not so stupid, so you have to know a lot of maths in order to cheat with banks. And now there are many mathematicians working with banks. They are very skilled, so it becomes very difficult. But this is a naive story. Of course, you cannot do what I'm proposing you, but just to give you the idea. So now, today, first, you owe an amount of money which is M. Let me call it M. And you decide to invest it. Okay, today you invest M. Today your wealth amounts exactly to M. And the interest rate, the yearly interest rate, is T. Okay? So in 1 year, so let me use the red here, in 1 year, you get M. Your initial amount of money, your initial investment, plus the interest. There is the interest rate is T, that has to be multiplied by your amount of money, M. So in 1 year you get M1 plus T. Okay, this is, I want to be precise, this T is the interest rate. And Tm, of course, is the interest. This is the initial investment. And after 1 year, you are here. Okay? Okay, this happens if you just invest this money. But try to do another strategy. Okay? So, an alternative strategy is the following. You get back your money from the bank after 6 months and reinvest it for other 6 months. And reinvest it for other 6 months. And then try to compute what is your amount of money after 1 year. Okay? So, after 6 months, you have M plus T over 2. You assume that if your interest rate is T in 1 year, then in 6 months is T halves. because we will talk about this hypothesis. But to be simple, do like that. The idea is that interest grow linearly in time. You fix the yearly interest rate, but then you start accumulating interest from the first day. And this is what banks say. So then you end up with m 1 plus t over 2 after 6 months. Then, what is different with respect to the previous behavior? The difference is that now you reinvest and your interest you accumulate it produces in turn other interests. So, after further 6 months, which means 1 year after the initial investment, what you have is your initial investment here, m 1 plus t over 2 plus what you invested, so which is m 1 plus t over 2 times t halves again. So what you have is you collect m, you collect 1 plus t over 2. What remains here is 1 from here and from here. Oops, sorry. Okay, I reconstructed. From here, you have another t over 2, so you end up with m 1 plus t over 2 squared, and then you can develop this squared, and then you have m 1 plus t squared over 4. Notice that thanks of this t squared over 4, this is larger, strictly larger than m 1 plus t, which is your final amount of money with the previous strategy. Okay, so it seems to be convenient to behave like that. Take back your money after 6 months and then reinvest it. Okay? Is it clear? Did you understand? If you did not understand, then stop the video, reread it, and re-listen to me, because it is an important passage here. But I have here to use a disclaimer. The disclaimer says basically that this is just theoretical. This is just theoretical because actual banks do not allow you to do like that. Why? How can they do? Because there are many reasons. First, in general, actual banks or fundings and so on, private societies, what do? They basically claim that your interest grow linearly day by day, but then if you get your money back before the end of the year, you don't have the right to have your interest first. Sometimes it is like that, and more often, I would say always, when you get back your money, you have to pay. You have to pay something. So this strategy is not so convenient. But from a mathematical point of view, let's keep the thing so clear. But I don't want really steal money from anyone. I want just to explain E. Non è per number. So, okay. And now you can try to put this strategy one step further. So instead of splitting your investment in two parts, so take back your money after 6 months and then reinvest it. You can split it in 3 parts with periods of 4 months. So another step, so the further step, is the following. First, invest M. Second, after 4 months, which is 1/3 of a year, get back your money. Then what you have? You have M plus M, your yearly interest rate. Since we assume that interest grow linearly, this is T over 3. So you get back M1 plus T over 3. Third, reinvest it. All your money, which is this M1 plus T over 3, and get it back after other 4 months. So what do you have? Okay, you have M1 plus T over 3 plus the interest that you have, which is just M1 plus T over 3, again T over 3. So you can write it like M1 plus T over 3 to the square. Okay, when you collect like before. Last passage, do it again. Reinvest all your money and take it back after 4 months. Therefore, after 1 year, you have M1 plus T over 3 to the squared plus your money, M1 plus T over 3 times T over 3. And this becomes 1 M1 plus T over 3 to the third power. And if you develop, according to the development of the cube of a binomial that you know very well, you have m1 plus t plus 3 t squared over 9 plus t cube over 27, and this is m1 plus t plus t squared over 3 plus t cube over 27. Okay, let us examine a bit this polynomial that we get, this polynomial in t. And so notice that you have 1 plus t, and this was the first strategy. This was just wait 1 year. And then the second, so this is larger than what happens with the first strategy, but the new point is that this is larger also than the second strategy, because the second strategy was 1 plus t squared over 4. And so already t squared over 3 is larger than t squared over 4, since t squared over 3 plus t cube over 27 is larger than t squared over 3, which is larger than this t squared over 4. Nice. So it is convenient, therefore, splitting in 3 is more convenient than splitting in 4. Sorry, than splitting in 2, not in 4, in 2. So, with the same computation, so by using the same reasoning, you get that splitting in 4 gives, so how much does it give? So let us see here, splitting in 1 gives m1 plus t, splitting in 2 gives m's 1 plus t over 2 to the second power. So notice that 2, the number of splitting that you make, appears here, the denominator inside the parenthesis under the t, and here in the exponent. If you split in 3, you get this final amount of money, which is t over 3, and 3 appears here under the t, and here appears here as the third power. So splitting in 4 will give you m 1 plus t over 4 to the fourth power, which is what? It is m 1 plus t, again, like splitting in 1. And then here we have 6 t squared over 16 plus 4 t cube over 64 plus t4 over 128. So this is m 1 plus t plus 3 over 8 t squared plus t cube over 16 plus t4 over 128. And notice that already this here is larger than the cube, t squared over 3, because 3/8 is larger than 1/3, and this is again larger than t cube over 27. So you know that this is larger than m1 plus t over 3 to the third power. So splitting in 4 is more convenient than splitting in 3, that is more convenient, or splitting in 2, that is more convenient than no splitting at all. It is still more convenient. So I was perhaps a bit pedantic here, but what I want to tell you in this introduction to it, okay, here I'm just introducing this very important chapter, which is E, is that, so by generalizing I won't prove that, but just use the intuition. Intuitively, splitting in n, the investment, the yearly investment in n sub-investments gives a final amount of money which is m 1 plus t over n to the nth power, okay, and that will be more convenient than using n minus 1 splitting. Okay, so the idea is that the more you split, the more you gain at the end. Okay, I won't prove this statement here. I think it could be proved by induction. I never did it, but I think. However, just intuitively, I will prove that it is more convenient, that the larger n, the larger at the end this guy. So in another language, that the sequence in n is monotonically strictly increasing. I will prove that. But now, the question is the following. How much money can I have from my bank? How much money can one have from the bank at maximum? This is the first important question, and in particular I want to know if I can have an infinite amount of money. So mathematically, the question is the following. First, is the sequence AN is equal to 1? So let us skip the t. No, sorry, the n. T over n to the n. Is the sequence AN monotonically increasing? We will see yes. The second, is it bounded? The answer is again yes. Unfortunately, we cannot steal an infinite amount of money. The third is, if it is bounded and monotonically increasing. What is its limit? The answer is e to the t. So the next chapter will be, the next video will be devoted to this problem with the t equal to 1.